Hello. This is part of the annoying calculation series for a basic calculus-based probability and statistics course. And I'd like to discuss the binomial coefficients and explain algebraically why they have to be integers. Now, initially, first of all, should just be a brief reminder of what they are. The notation is sometimes written like n choose r, where r is less than or equal to n, greater than or equal to 0, or sometimes written n combinations r. And it's often described as the number of ways to select r unordered items from n distinct items. Okay, that's a standard way it's described. Now, how the intuitive way to derive the formula for it is, let's say you have n items and you want to select r, so make r a slot. So this is r slot 1, slot 2, slot 3, all the way out to slot r. Now, the first one you can fill with n items. The second slot, since you've taken one item out of the mix, you have n minus 1 items you can select for the second, n minus 2 for the third, and so on. And at the almost the last one, it's n minus r plus 1 items there. Now, so the number of ways you can select an ordered list is going to be n times n minus 1 times n minus 2, all the way out times n minus r plus 1. But if we were to continue this as a factorial, this would be the same thing as n factorial divided by n minus r factorial. Now, that's easy to see why that's an integer, because here you're multiplying the first all from 1 to n. Here you're multiplying from 1 to n minus r. So when you do the division, it's clear that you get an integer. But this gives a specific order. So we now divide by the number of ways of permuting our items, and that's r factorial. So we end up with our formula, combinations of r from n, or n choose r, equals n factorial, n minus r factorial, times r factorial. But then the question sometimes crops up is, how do you know that r factorial divides n factorial divided by n minus r factorial? So how do you know you actually get an integer there? Now, intuitively, you'd say, well, it's counting something, and you can only count an integer number of ways. But let's nail this down precisely. And so one way we can do this is we can start by defining for n equal 1, we can define 1 choose 1 to be 1, and see 1 choose 0 to be 1 as well. And that makes sense, right? The number of ways you can choose one item from 1 is 1, and the number of ways you can choose 0 items from 1 is also 1. Next, say that for n higher than 1, for n greater than 1, we'll say that n choose 0, we'll declare that to be 1. See, n choose n to be 1. And that also makes sense. The number of ways you can select 0 items from n is 1, and the number of ways you can select n items from n is 1. No problems there. The next thing we do is we show that if we take Cn minus 1, k minus 1, plus Cn minus 1, choose k, that we get this relation here. And this is sometimes called the Pascal's relation. And we'll show why in just a little bit. And here, of course, the understanding is that k is between 1, 2, and minus 1. So this thing makes sense. And if we could show this relation, so if we can show this, we will show that all C and K, where K is between 1, 2, and minus 1, is the sum of integers. Inductively. Because if we show this at this level, then it must be true for all previous levels. So, and the sum of integers is the sum of integers. So that's what we must, this is one way to do it. So let's get started on doing that. And the very first thing is I'm going to translate this thing right here. I want to go ahead and select it. So just going to translate this formula here. Let's see if I can do this without moving it. Oh, that's not what I wanted to do. So I'll just rewrite it. I won't be so lazy. So I'll just rewrite this as, I'm going to rewrite Cn minus 1, k minus 1, plus Cn minus 1, k, right as, and let's write the definition carefully. N minus 1 factorial, k minus 1 factorial. Now let's be careful here. This is n minus 1 minus k minus 1 factorial, and this is division. Then we have n, well, let's just keep this in the same order. So we'll have the k factorial here, and then we'll have n minus 1 minus k factorial here. And I want this to equal something. Now we do the old common denominator. And let's just see what we get here. Now this is going to equal n minus 1 factorial. Now the k minus 1 factorial, I can do something with that. I'm going to multiply that by k minus 1 factorial, and I'm going to multiply this by k. Now this thing here, I'm just going to do a little bit of algebra. N minus 1, and this is subtract, this is a parenthesis here, k minus 1. That turns out to be n minus k. Then you have a negative 1 minus, so you have n minus k. Then you have a negative 1 minus a minus 1 because you're distributing it right here. You're distributing that plus n minus 1 factorial, k factorial. And here you have a n minus 1 minus k factorial. I'm going to do something with that. And let's just see right here. And we're going to figure out what to do when we do this. This is k, n minus 1 factorial. Now k times k minus 1 factorial is just k factorial. So we got these things. That's good. The interesting thing here is that we have an n minus k. Oh yeah, this is factorial, of course. We have a -1 minus a -1. Cancels. So now we have this. Well, this part right here is really n minus k -1. That's just a change in order. That's okay. So to make this, that's what this is equal to right here. So I'll just write that down. And now I get the second part of the common denominator. I'm going to multiply this by n minus k. And multiply this by n minus k. See, this is n minus k -1. So now, by doing the common denominator, I get the following. I get k n minus 1 factorial, k factorial, n minus k factorial, plus n minus 1 factorial, n minus k. The bottom is a k factorial. These two are now n minus k factorial. See, remember, there's a factorial here. We now have a common denominator. And then that leads us to the denominator we want. And now I have an n minus 1 factorial that I can factor out. And I'm left with a k plus n minus k. And notice these two k's cancel. So we have n minus 1 factorial, n k factorial, n minus k factorial. And that leads us to exactly what we want. That leads us to, in fact, if you recognize this, this is now n factorial, k factorial, n minus k factorial. And by strict algebra, that's n choose k. So now that we know that's true for all n greater than or equal to 2, this is a sum of integers and therefore must be an integer. So that proves the result right there. I don't want to do that. So I'll call this, I'll just antiquated thing. That's what happens when you're let's just say this. Save it as, let's see, binomial. Now let's say a little bit more. Now we've already proven that. So we've shown that n choose k equal or c n, or I used r, is an integer. Now this relation here that we just proved, the reason why it's called Pascal's relation is that you can start as follows. Start with this thing here and call that a 1. Then go down one level and call that a 1, and that's a 1. So this is the 0th level. This is the 1th level. Call this a 1, call that a 1. Now 1 plus 1 is 2. And then we put a 1. 1 plus 2 is 3. 2 plus 1 is 3. And this is a 1. Now, the way to think about this is that the very first row would be x plus y to the 0, which is just always 1. The second row, row 1, is x plus y to the first, So the coefficient of x is a 1 and the coefficient of y is a 1. The second row is x plus y squared. That's x squared plus 2xy plus y squared. There's a 2, there's a 1, and then a 1. Now, if you put x plus y cubed, we can read off what you get. X cubed plus x squared y times 3 plus 3x y squared, there's a 3, plus y cubed, and so forth. So, and again, I ran myself out of room here, but that would be a 1, 4, 6, 4, 1. We can see right here that this is a nice demonstration, this Pascal's triangle. Which goes down, and you can make that go down as far as you want. Well, what you see is that we could define C and R or C and K inductively, starting with the first row. Or with row 0 and row 1. Then you can define this inductively. And the reason that matters, and this is, we're going to get a little bit beyond probability statistics here, but suppose you have x plus y to the nth power, but we are working in a commutative ring. Well, a commutative ring, and basically what that is stuff like the integers that you just, there's addition, subtraction, there's a 0, there's a 1, there's a multiplication, but there's not necessarily division, not for all elements. So you might not have the notion of dividing by something. So if you wish to define the binomial coefficients to be the coefficients you get if this is working over what's known as a commutative ring, you can get the coefficients by stating what they are. I mean, early on, for let's say the x plus y to the first power, using the distributive law and the commutative law to get the next ones. And then the Pascal's relation is strictly a ring addition relation. You don't have to rely on the n factorial divided by k factorial, n minus k factorial thing, which might not exist in a ring. So what we've actually done is we've shown what you get by this formula here. Is the same as what you get from the Pascal's relation. Where this is defined as the sum of the previous two, which have been defined at the beginning. So that's my little spiel about the why the binomial coefficients are necessarily integers, and thanks for watching.